Alrighty, in this particular chapter we moved away from just the basic properties of charge and force and take up the idea of energy and its relationship to work. So we start off in this section dealing with electrical potential energy, which, from our definition, is another form of mechanical energy that is, again, like gravitational, an energy associated with location or position. For gravitational potential energy, what was your position in a gravitational field? Electrical potential energy, what is your position in an electrical field? So if I change my position in a gravitational field, that related to work done on or by an object. And it's the same thing for electrical potential energy, as we'll see. Changing your position in an electrical field means work was done by a charge or on a charge. When we look at the idea of that electrical field, we do have to decide whether it's a uniform field or whether the field is non-uniform. In a uniform field, we see something very much like the diagram we have in figure 18-2, where each of our lines is equidistant from the other and they're all pointing in the same direction. If I put a positive charge, like we see for A, in that field, he would have some amount of electrical potential energy with respect to a 0 point. And that 0 point is arbitrary. I can pick it wherever I want, just as we did for gravitational potential. Usually, it's considered the start of the field. So wherever the field starts, wherever my lines are right here, where they begin, is sort of considered the 0 point a lot of times for a uniform field. Now, if that particular charge moves, say from point A to point B, that change of position would be associated with a change of electric potential energy. How much did it change? Well, there's your formula right there that would help you figure it out. What's my charge? Is it positive, negative, and what magnitude? What's the electric field strength? And how far was the displacement? Now, that negative sign that you see there is there for two reasons. One, it takes into account if the motion is based on a positive or negative charge. And also, it helps us work with the idea of displacement. So if we see the figure again, 18-2, right here we have a positive charge. We see the little positive charge right there. If he moves in the direction of those field lines, he's going away from the positive. Remember, field lines are always drawn in respect to what a positive charge would experience. He would be getting away from the source of the field, and therefore his potential energy would go down. Putting that in the formula, a positive Q and a positive E and a positive D, I get a negative electric potential energy. He lost energy. That's just like rolling down a hill for gravitational potential energy. You lost some. If, however, I moved him from B to A, he would gain electrical potential energy. I would be pushing him towards the source of this positive electric field. Pushing two like charges together requires work, and that means I've given him energy. So I would have a negative D, which would give me a positive electrical potential energy. Turn this around for an electron. This was an electron instead of a positive charge. Moving in this direction from A to B, he would be moving away from the positive source of the electric field. Well, when you move like charges apart, energy goes down. But unlike charges, energy goes up. It takes work to separate unlike charges. So, with my negative Q right here, and the negative sign there, I'd have a positive electrical potential energy. An electron would gain energy moving from A to B. Turn him around, go from B to A, he's now rolling down his energy hill. He is going from a higher potential energy state to a lower one. Yes, I still have a negative Q, but I also have a negative D. The outcome, a negative potential energy. Now, this equation is only good for a uniform field. And one last little thing, this displacement, remember, is in respect to parallel, I didn't quite highlight the way I wanted to, but that's okay. It's in respect to a parallel displacement with the electric field lines. So going from A to B, that displacement counts towards changing electrical potential energy. But going from B straight upwards or straight downwards, A straight up or straight down, that's not going to cause any changes. That's like walking across a horizontal floor for gravitational potential energy. No change will be observed. Now, what happens if you don't have a uniform electric field? Let's say you have a pair of charges where our field is most decidedly non-uniform. Well, then I do have to use a different equation. The potential energy associated with a pair of charges would be relevant, or I should say in respect is a better term maybe, to the size of the charges involved and the separation distance. Formula looking a lot like Coulomb's law, but notice that r in the denominator is not squared. So for electrical potential energy, one, make sure is it a uniform field or are they point charges, and then use the appropriate formula to actually solve, keeping in mind our signs for charge and our signs for displacement. But now, electrical potential energy sometimes is not really as useful to us as another concept called electric potential. For electric potential, this is an idea where I take the electrical potential energy and I look at it with respect to the size of the charge involved. So electrical potential, what's my electric potential energy divided by my size for Q? Now, at any point in an electric field, the bigger the Q, the bigger the electric potential energy. And that ratio winds up being the same regardless of the size of the charge I put in that spot. So electric potential is independent of the charge at any particular point. Whether it's a big charge or a small charge, the ratio stays the same. Now, moving that charge from one location to another will change the electric potential. And so we can then have another term that we call potential difference. And this guy's a big one because this guy also goes under the term voltage. And voltage is a term everyone knows, everyone recognizes, and we will get to it a lot in the next couple of chapters. With potential difference, I am looking at 2 points in an electric field, and I want to know what's the difference in potential energy now per unit charge. How did my electric potential change as I went from one location to another? Yes, it could be positive or negative. My potential energy could have increased. It could have also decreased, and that's okay. My negative electric potential, my negative potential difference versus my positive would give me that indication. So for potential difference and electric potential, the unit is the volt, which is equivalent to joule per coulomb. And sometimes it's good to think of it that way or remember it that way. How much energy per unit charge am I looking at in this particular situation? And how much energy per charge did I see change as a result of the motion of a charged particle? So if you have a 1.5 volt battery, my charge gained or lost 1.5 joules per coulomb of charge. 12 volt, I gained or lost 12 joules of energy per coulomb of charge. Now when we're looking at calculating potential difference, again, we do have to take into account, is this a uniform field or are we dealing with point charges which don't have uniform fields? If it's a uniform electric field, my potential difference would simply be based on the strength of the field and displacement. And again, there's that negative sign to help us sort out the direction of motion and the type of charge we're dealing with. If, however, I have a point charge, the situation is a little different. With a point charge, I still need some reference point, and that reference point is often considered infinity. And that actually effectively sort of washes it out of importance in the problem if you want to think about it that way. So if I wanted to know what's the potential difference near a point charge, what we're actually saying is if I took a particular charge, let's say, who knows, B over here, what is the potential energy at some point near him? I'm actually saying how much energy would it take if I moved the charge from that point to infinity or from infinity to that point. Ultimately, it's going to come out to be the same value, just difference in sign. And if we think about it, the bigger the charge would have I'd need more or less work to actually move him, but also the bigger the distance. A space close to the charge is more distant, perhaps, than one very, very far away from the charge with respect to the idea of infinity. So the closer I am to a charge, the stronger, perhaps, I would expect to see the electric potential or the potential difference in this case. The farther from the charge, I would expect it to be smaller. And if we look at our formula, the potential difference near a point charge grows as the size of the charge grows, but lessens as the distance changes, specifically as it gets larger. Now, the nice thing about electric potential is that even using the superposition principle, when I have multiple charges in a situation, this guy is scalar. Things dealing with energy are scalars, and therefore now I do not have to worry about the vector techniques that we used in the previous chapter dealing with electric force and electric field. So in a case like this, where I want to know what is the potential difference at a certain location based on the actions of two charges, not a problem. Run my formula, KQ1R1 for one charge pair. Run it again for the second charge pair. And yeah, I would have to use Pythagorean theorem to find out R sub 2. But when I get those values, all I have to do now is add. I don't have to then turn around and break, for example, this guy right here into its components. For batteries, you should definitely know their function. They serve as a source of potential difference. One end of the battery, something up here, would have a low potential energy. In fact, he would be considered the 0 point for looking at the electric potential. Other end of the battery, that's a high electric potential end. So for a 1.5 volt battery, which these little batteries, actually all of these three here, but not the 9 volt, those would have 1.5 joules per coulomb electric potential at one end, the negative end, and 0 joules per coulomb at the positive end. So I do need a 0 point, and for batteries it's considered the positive terminal. When we talk about conventional current in the next chapter, we might kind of flip that around a little bit, but we'll talk about the why. In a bigger circuit, like a household circuit, our 0 point is considered the ground, and we talked about grounding in class, the point where you could dump as much charge as you wanted to and it would not change the electric potential. So for a household circuit or bigger circuit, we will have a ground somewhere serving as our 0, by which we measure then the high electric potential point. So charges go from the high electric potential end of the battery to the low if I connect a wire so that the charges could move, and anything in their way, like a light bulb or something, the charges could do work. The battery then turns around from the low electric potential end and fuels the charges back up to the high electric potential end. So the battery is doing both. It's allowing charges to do work by providing that energy hill for them to roll down, but it's also then shoving them back up the energy hill so that they can have another go-round. Then we got to the idea of capacitance. Capacitance sort of links the ideas of charge on an object and the potential difference that it's experiencing. For objects, the property of capacitance is the ratio of charge to potential difference. So, for something like you, alrighty, given your conditions right now and assuming they don't change, you have dry skin and dry hair and your body composition is a certain thing, etc. If I exposed you to a potential difference, that would equal so much charge that your body would be exposed to, and vice versa. Expose you to so much charge, there would be a fixed potential difference that your body would experience. And it is a fixed ratio. So for any type of an object or something, I can look at the potential difference and how that charge is related to it. Now, a capacitor is a device. Capacitance is a property. Capacitor is a device. Capacitors are there specifically to act as storehouses of charge and electrical potential energy in a system. And the simplest was a parallel plate capacitor. In a parallel plate capacitor, which basically over here A, B, and C are all examples of, I have just that, two parallel plates. Two conducting plates that are separated in this gap by some form of insulator. Could be air, could be something else. When the plates are just standing next to each other, they are neutral. They have an equal number of positives and negatives. But once I hook them up to a battery, a source of potential difference, charges from one plate will migrate to the other. And so what I'm going to start to see is as I start to charge, small charges begin to build up on each plate. Electrons leave one and accumulate on the other. When they're fully charged, then At that stage of the game, my charges are kind of stuck. And by that I mean this. I either have maintained a potential difference, which will keep these charges from rolling back, because now my energy hill, effectively, they've been pushed in one direction, and that push still exists if the battery's still there. Or if I unhook the battery completely, these charges are stranded. And as long as they're stranded, I have a potential difference between one plate and the other. If I hook these up with wires, the charges would flow down that potential difference. The plates would become neutral eventually, of course, and therefore be unable to do any work at that point. But while the charges are separated, there is an ability to do work. And that ability to do work could be captured by a device like a light bulb or something along those lines, and I could get something useful out of it. So with the capacitor, while they are just simply sitting side by side, no net charge on the plates, the charging process separates the charges, so I have a net negative and a net positive plate. They will remain like that until they are connected by a conducting wire, in which case then the charges are free to move and therefore do some work. Now, capacitance is based on the size, shape, and design of your capacitor. Ultimately, the amount of charge you store per potential difference, or divided by potential difference, is how we define capacitance. And then, looking at the size, shape, etc., I can figure out how to construct the capacitor so that I get the capacitance I want. So if I'm going to hook a capacitor up to a certain size battery, and I need it to hold so much charge, that tells me the capacitance I'm shooting for. This formula, bottom formula, tells me then how to build the capacitor to get the capacitance that I need. We see that the capacitance of a capacitor, in this case a parallel plate capacitor, but it's a similar situation for other types of capacitors, is based on three things. One, the area of the plates. Make them bigger, you are able to store more charge. Their separation distance. Put them closer together, you are also able to store more charge for the same potential difference. You're actually increasing the strength of the electric field. And this value, called epsilon sub 0. Epsilon sub 0 is permittivity of a vacuum. This is a permittivity constant. The little 0 tells me it's specific for a vacuum. Without the 0, it would be for any substance out there. He does have a value. It is a constant. It will be given to you on a formula sheet, but don't confuse him with Coulomb's constant. And what this says is, in a vacuum, where I would have nothing between the plates, plates of a certain size and a certain distance, with that information, I can figure out exactly the capacitance. So I could build the capacitor the way I wanted to. If I'm limited on size and spacing, changing this value from a permittivity of a vacuum to a different value by choosing another insulating material between the plates would increase my capacitance. And we'll talk about dielectrics in a minute. When we're looking at the idea of my capacitors, one thing we had brought up in class was that spheres are great capacitors. And that's because when you increase the diameter of a sphere a little, surface area increases a lot. So something like the Earth is a massive capacitor. It's a tremendous capacitor. For it to actually see a change of electric potential, in other words, change its potential difference, the amount of charge it has to gain or lose is mind-boggling. So the Earth can take an almost unlimited number of excess charges or lose an unlimited number of charges, and we're not going to change its potential difference. Therefore, we can all really say its electric potential is 0, and that's why it serves as a great ground. Now, I said that between the plates of your capacitor, you can have a vacuum or air, which we use the same value of the permittivity of free space or the permittivity of vacuum in problem solving. But if you need to bump up the capacitance more, we can put in a different type of insulator, and they are generically called dielectrics. Dielectric is an insulating material, and it can take a variety of forms: air, rubber, glass, ceramic, fabric, whatever it happens to be. And when you put it between your plates, the capacitance will go up. This would allow you for a set capacitor to increase its capacitance. So for example, this guy right here in figure 18-7, just sticking a dielectric in there would increase his capacitance. I could even then maybe take another step. I could go ahead and push the plates closer together, and that would give me another boost to the capacitance. What dielectrics do is they help reduce the size of the electric field. That allows me to put more charges on without seeing a change in the potential difference. It also helps with what we call electrical breakdown. In electrical breakdown, you get such a potential difference that charges can actually distribute themselves back from the negative plate to the positive, i.e., you see the jump of a spark. We don't want that. It's not a good thing. So a dielectric can serve two purposes. One, it can protect your capacitor from damage due to a spark, and it can also increase its capacitance. Now, when my charges are separating, that process is called charging. When the charges are now allowed to redistribute back to their original plates, in other words, the plates are allowed to become neutral again, that's called discharging. And when we take a look at the curves for charging and discharging, we saw a very characteristic pattern in our book. You saw that the discharging occurred extremely rapidly in the beginning, and so did the charging. Well, that kind of makes sense if we think about what's going on. During charging, charges from one plate, which was the positive plate right here, moved on to the negative plate. Originally, I had effectively no excess charge over here. So as electrons began to flow over, there was plenty of space for them to move around. There wasn't a high density of charges, and therefore the forces of repulsion were pretty low. But as more and more charges built up, that force of repulsion built. It became harder and harder to shove more charges on, and therefore charge motion slowed down. Well, for discharging, the second I reconnect a wire to these two plates, these electrons come rolling down the hill as fast as possible. There is a big potential difference. There is a big force of attraction. They really start to move quickly. But as more and more negatives accumulate back on this plate, the charge difference between these two is lessening. There's less of a force of attraction, and there's less of a potential difference. And charge motion slows down again. So I saw those nice exponential curves where charging, we saw it rapid in the beginning and then tapering off, ultimately to a maximum where I just couldn't shove any more charges on. Discharging, very rapidly at the beginning until it slowed down and slowed down and slowed down. So finally there was no more net charge motion because the plates were now neutral. In terms of what capacitors are used for, you might remember a few things, such as they're used in computer keyboards, they are used in turn signals, they are used in the flash bulbs of cameras. Anytime I need to store charge to be released when I want, in other words, release on demand. And for something like a flash bulb, I want them to release rapidly, so they give me a big, big, big flash. Now, the other thing about capacitors, of course, we can't forget, is they do store charge, sure, but they're also really storing energy. Once I have separated charges, I have a source of potential energy because of that potential difference. How much energy? Well, it depends. How big of a charge do you have? And what's the size of your potential difference? Looking at those two would give me one way to calculate electric potential energy. But there were a couple other formulas your book threw at you, and these formulas were quite useful in problem solving. Again, depending upon what variables do I have. Do I have Q, do I have V, or do I have C? Who do I have here? That would allow me then, looking at the problem, to go ahead and solve for electric potential energy. Now, when you're dealing with all of this, in this chapter and in the previous chapters, just keep your eye always on units. Charge, coulomb. Don't confuse that with the big C here, which means capacitance. Capacitance unit is the farad, capital F. And of course, V, his unit is also the volt. I find sometimes working with the problems between the last chapter and this chapter, big C for capacitance gets confused with big C for coulomb. And for some reason, when people are solving for charge, they'll go ahead and give me the Newton as the unit, or solving for force, they'll give me coulomb as the unit. So just pay a close bit of attention to that as you're doing your problem solving. Your problems for capacitance are generally pretty straightforward. Using the four formulas actually we just had back there in the past few pages. Just don't forget, for problems like this, for example, where I have a part A asking for charge in the plate of each capacitor, given this capacitance and this battery. For part B, we change the battery. So the charge I solved for A is not valid to use in part B. I'd have to either go back and solve for it again, or pick a formula, in this case for electric potential energy, that didn't involve charge. Alrighty, so make sure going through electrical potential energy, potential difference, and electric potential, capacitance, batteries are involved in here, and of course always the idea of work. Don't forget your units. Be sure to recognize them in problems and use them when you have problems and you have to provide the unit. You know I'm taking off points if you're not putting units down in your short answers, so don't lose points just because of that.